In the previous video, we saw that our common drain amplifier had a voltage gain of about 1, and really we said it was actually a little bit less than 1. And so first of all, let me come back and say something about the notation that I forgot to mention in the previous video. And with that voltage gain being 1, and the output voltage being defined at our source, we can then say that the source voltage follows the input voltage. So this is the reason you'll often hear a common drain amplifier referred to as a source follower, because the source voltage is following the input voltage. But going back to the question we had at the end of our previous video, why is this configuration useful if we have a voltage gain of about 1? So how could that possibly be helpful to us? And so in order to answer that question, what we're going to do is we're going to investigate our output resistance. So our output resistance, and so in order to do that, we're going to utilize a method we've seen before, which is our test source method. So let's take our small signal equivalent circuit that we talked about previously, and what we're going to do now is at our output, we're going to apply some test source. So let's get rid of some of this, and let's change this to a different color, and we're going to apply some test source. And as we're doing this sort of in calculations, it doesn't matter if this is a test voltage or a test current. In this case, I'm going to do a test voltage just because that's typically what we would do in a lab setting if we were actually testing this circuit. And so we're going to say this is some arbitrary voltage Vx, which creates some current Ix. And so that means that our output resistance then is going to be equal to Vx over Ix. And so as we've talked about before, sometimes you'll see people say, let's adjust this until we have some current that's equal to 1 amp, and that way you're just solving directly for Vx. Personally, I like to keep it in our general variables, but again, that is personal preference. So one important thing we need to remember is when we're doing this test source method, we need to deactivate any independent sources. So our test source method, what we need to do is we need to deactivate any independent sources. And so in this case, we have one independent source, which is our VI over on the far left. So what we're going to do is we're going to get rid of this guy, and if we want a voltage source to go to 0, which is what we would do when we deactivate it, we're just going to replace it with a short circuit. So we no longer have this VI voltage here. And so what we can see then is that's going to result in 0 current over here in the left side of the circuit. So we can essentially ignore everything that's going on over there, and we're going to focus on the right side of our circuit. So let's analyze our right side by using KCL at this top node up here. So let's do a KCL equation. And so we see we have a couple currents coming in, and then because we have this voltage, which is our Vx here, we're going to have a couple currents going down through these resistors. So KCL, sum of currents in equals sum of currents out. So coming into that node, we have GM VGS as well as our test current Ix. And that's equal to the sum of the currents leaving, which is going to be Vx over R naught plus our Vx over Rs. Now what we can note is that because we have 0 current over here, of course we're going to have 0 volts dropped across this resistor, or 0 volts for our Vn, whichever way you want to think about it. But basically we can do a Kvl loop, and we can say that our Vx is going to be equal to negative VGS, and then of course that's just 0. So we get something that looks like this. So we can say we have VGS is equal to negative Vx. So I've just kind of swapped that around from how I said it earlier. And so that's because we're going to substitute for this VGS here. So when we do that, we can move that negative GM Vx to the other side of the equation. And what we're going to get is Ix is equal to Vx, which is in all of those terms now, so we can factor that out. So that's going to be Gm plus 1 over R naught plus 1 over Rs. And now we can find what we're looking for, which was that ratio of Vx over Ix. So we can say that our output resistance, R naught, is going to be equal to Vx over Ix, which is equal to 1 divided by that Gm plus 1 over R naught plus 1 over Rs. And so we know this is really similar to our parallel combination formula. So we are inverting the sum of the inverses of resistors. But of course this GM is sort of the exception. But if we define some value 1 over Gm, we can say that our output resistance of the amplifier is just equal to 1 over Gm in parallel with our small signal output resistance of the transistor in parallel with our source resistor Rs. And so what we're going to see is typically this first term is going to dominate because it's going to be the smallest. So typically dominates our overall output resistance. And so to see that, let's consider some values from an example. So we're not going to look at the full example, but for some extra practice, you could definitely take a look at that. So this is coming from example 4.9 on page 232. And from that analysis, we get that our Gm is 11.3 milliamps per volt. Our output resistance of the transistor is 12.5 k ohms. And our RS value is 0.75 k ohms, or 750 ohms. And so if we plug into our output resistance formula, we see this is going to be R naught is equal to, and I'm going to leave everything in terms of milliamps and k ohms, so I have 1 over 11.3, which is going to be in parallel with 12.5, which is in parallel with 0.75. And so in this case, we end up finding that this is approximately equal to 78.7 ohms. So what we notice is that this is a relatively small output resistance. So we have a small output resistance of our amplifier, R naught. And so this is something that we should have anticipated from when we looked at that summary table, sort of as we were starting to talk about our MOSFET amplifiers. And so ultimately what this means is that if we use this as the output stage of a multi-stage amplifier configuration, we're going to have minimal loading effects. So minimal loading effects at our output, which again is desirable if we're using this, for example, as a voltage amplifier. And so another way to say that is that this acts more like an ideal voltage source. An ideal voltage source would have 0 output resistance. So acts more like an ideal voltage source. And so of course that's compared to something like a common source configuration where we had a moderate to high output resistance, in which case we would have relatively significant loading effects. But of course our loading effects are ultimately going to depend on what our load resistance R sub L is. And so we can go back to our basic circuit representation. If this is some output resistance of our amplifier, so V out amplifier, and then we have some output resistance of the amplifier and some load resistance in parallel, so this is R naught and this is RL. Well, if we want this overall V out to be as close as possible to our V out amp, then we want this R naught to be small.